This video is about determining the relative acidity of a salt solution. The key point here is to assign the acid-base properties of the cation and the anion. Depending on the situation, some of them are relatively easy, others are more complicated. The most important thing about these types of problems is to follow the steps of the strategy in order. It really does matter here. Before we do any predicting, we need to know which ions we're dealing with. So write the chemical formulas with charges for the cation and the anion. My experience is that if you skip this step, it's more likely you won't be able to figure out the problem. Then do an initial assessment of the cation and the anion. Is the cation a weak conjugate acid? If you remove an H+, does it become a weak base? If so, then the cation is a weak conjugate acid. If the cation is a small, highly charged metal ion with a 3+ charge or higher, then it behaves as a Lewis acid. For the anion, if you add an H+, does it become a weak acid? If so, then the anion is a weak conjugate base. Is the anion amphiprotic? There must be an H present for this to be the case, so check for that first. Then, two things must be true. If you remove an H+ from the anion formula, is it a weak base? If you add an H+ to the anion formula, is it a weak acid? If both of these are true, then the anion is amphiprotic. After this initial assessment, there are three strategies to determine relative acidity depending on which ions have acid-base properties. One ion or neither ion, both ions, or the anion is amphiprotic. If the cation is a conjugate weak acid or a Lewis acid, the solution is acidic. If the anion is a conjugate weak base, the solution is basic. And if neither ion has acid-base properties, the solution is neutral. If both ions have acid-base properties, then we need to compare the Ka of the cation to the Kb of the anion. The larger equilibrium constant determines whether the solution is acidic or basic. If they're equal, then the solution is neutral. The final situation is if the anion is amphiprotic. Start with the chemical formula for the anion and look up the Ka. This gives us the Ka for the anion acting as a conjugate acid. Then we need to determine the Kb for the anion as a conjugate base. First, add an H+ to the original anion formula. This gives us the chemical formula for the anion's conjugate acid. Do not skip this step. Look up the Ka for this new chemical formula. Now we're going to use this new Ka to calculate a Kb for the anion as a conjugate base. Finally, we compare Ka to Kb, and the larger value determines whether the solution is acidic or basic. If they're equal, then the solution is neutral. I really cannot stress enough how important it is to follow all of these steps. So we'll work through several examples where we have a particular solution and we want to determine if it is acidic, basic, or neutral. Now for all of these examples, there are molarities included. The goal, though, is not to use those molarities to calculate pH. That's not what we're trying to do here. We're just going to look at the chemical formula to make our determination. So our first solution is FeCl3. The first thing we need to do is write down the chemical formulas for the cation and the anion. So the cation is Fe3+, and the anion is Cl-. We notice that chloride will have no effect. So whenever we see the conjugates of a strong substance, when we see the conjugate base for a strong acid, for example, chloride, bromide, iodide, those will have no effect. When we see a cation, such as sodium or potassium, those also will have no effect. We cannot add or remove an H+ to these types of ions and end up with a weak substance. So the chloride has no effect. The iron 3 we recognize as a highly charged cation, and that tells us that we have a Lewis acid. So that's the first thing we need to do, is just assess the ions to determine if any of them have acid-base properties. So in this example, only the cation does, because the cation is a Lewis acid. And because the cation is a Lewis acid, that makes this solution acidic. So in this example, our cation is NH4+, and our anion is NO2-. At first glance, we don't see any chlorides, bromides, sodium, potassium, anything like that. So it appears that both ions have acid-base properties, but we're going to figure it out. This is one of those situations where if you are not really careful, it is easy to make the wrong determination. So before we do any of the work, let's note what it is we're looking for, what we need. We need to look at the Ka for ammonium ion, and we need to look at the Kb for nitrite. Recognizing this will help us keep in check what it is we need to do. It's going to seem like we're adding some extra steps in here, but we're not. So the first thing we do to actually try to figure this out is we look at the cation and we remove an H+ to get the formula for the conjugate base. When we do that, we end up with NH3. We're going to do the opposite for the anion. So over on the anion side, we're going to add an H+ to give us the chemical formula for the conjugate acid, which will be HNO2. So now let's look at the information that we do have. We have a Kb for ammonia, which is 1.76 times 10 to the negative 5. And we have a Ka for nitrous acid, which is 4.6 times 10 to the negative 4. Now the tendency at this point is to compare this Kb with this Ka. But that's not what we need to do. I'm going to remind you of what we said we did need to get, and that was a Ka for ammonium and a Kb for nitrite. The values that we have right now aren't those. We have a Kb for ammonia, but what we need is the Ka for its conjugate acid, so we'll have to calculate it. On the other side, we have a Ka for HNO2, but that's not what we need. We need a Kb for NO2-, so we'll have to calculate it. So for both of these calculations, we'll use Ka times Kb equals 1.0 times 10 to the negative 14, and rearrange it as needed. So for the cation, we want to calculate Ka, so we have Ka equals 1.0 times 10 to the negative 14 divided by 1.76 times 10 to the negative 5, rounding to 2 sig figs, gives us 5.7 times 10 to the negative 10. For the anion, we need to calculate Kb, which will equal 1.0 times 10 to the negative 14 divided by 4.6 times 10 to the negative 4. Also, to 2 sig figs, the calculation gives us 2.2 times 10 to the negative 11. So in this example, the Ka for our cation is greater than the Kb for the anion, and this solution is acidic. In our next example, we will write down our cation, which is sodium, and our anion, which is nitrate. Sodium will have no effect. There's no hydrogen to remove to form a conjugate base, and it's not a Lewis acid. Nitrate, you might think, okay, I can add an H+. So let's just look at that. If you add an H+ to the anion formula, we end up with HNO3. So while it's true that HNO3 is an acid, it is a strong acid. And by definition, strong acids dissociate 100%. So even if you could combine them into the acid formula, they're going to separate or dissociate right away. So this ion, also no effect. So because both ions have no effect, this solution will be neutral. In this example, we have sodium acetate. So we're going to write down our cation and our anion. The cation has no effect. We've already discussed what happens with sodium. For the anion, if we add an H+, we get the formula HC2H3O2, and that is the chemical formula for acetic acid. Acetic acid is a weak acid. So that tells us that our original anion is a weak base. So in terms of acid-base properties, no effect for the cation, a weak base for the anion, and this solution will be basic. And our final example, we have the ions Na+ and HCO3-. Next, we notice that sodium has no effect, but we have to take a closer look at the anion. We notice that the anion already has a hydrogen, so it seems like that anion might be amphiprotic. If I add an H+ to that chemical formula, I get H2CO3. If I remove an H+ from that formula, I end up with CO3 2-. That tells me that bicarbonate, HCO3- is amphiprotic. So I have to take that chemical formula for the anion and determine a Ka for it acting as a conjugate acid and a Kb for it acting as a conjugate base. So the first thing I do is start with the original formula. So I have the formula for bicarbonate. I'm going to look up the Ka for that formula, and it's already listed here. The Ka equals 5.6 times 10 to the negative 11. Now, as I've listed the Ka values here within this problem, you can see that they're noted as Ka1 and Ka2. We don't need to worry about whether it's a Ka1 or Ka2. We're assessing bicarbonate in a very specific way for this problem. So bicarbonate as an acid, in other words, it's able to donate a proton, has a Ka value of 5.6 times 10 to the negative 11. That part is actually pretty straightforward. It's the next part that can get tricky. So now we're going to add the H+ to bicarbonate, and we get the chemical formula H2CO3. Now H2CO3 has a Ka. The Ka, which is shown, is 4.3 times 10 to the negative 7. But that is not what I need for this part of the problem. What I need is a Kb. I need the Kb for the conjugate base of H2CO3. And the conjugate base of H2CO3 is bicarbonate. So I need to calculate this. So I use the formula Ka times Kb equals 1.0 times 10 to the negative 14. I'm calculating a Kb, so Kb equals 1.0 times 10 to the negative 14 divided by the Ka for the conjugate acid, which is 4.3 times 10 to the negative 7. This calculation will be rounded to 2 sig figs. When I do the math, I get 2.3 times 10 to the negative 8. So what I'm comparing is the Ka for bicarbonate to the Kb for bicarbonate. So the Ka for bicarbonate is 5.6 times 10 to the negative 11. The Kb for bicarbonate, we just calculated that, is 2.3 times 10 to the negative 8. The Kb is greater than the Ka, so this solution is basic.